Hello students, welcome to our today's lesson. In our today's lesson, we will learn preparation of solution and colligative properties of solution. At the end of this lesson, you will be able to define dilution, define colligative properties, list colligative properties, calculate osmotic pressure, vapor pressure, boiling point elevation and freezing point depression. Preparation of solution, diluting solution. Dilution is the procedure of preparing less concentrated solution from a more concentrated solution by adding water. In the process of dilution, concentration and volume change, but number of moles of solids and number of equivalents of solids remain unchanged. Therefore, number of moles of solids is unchanged in the process of dilution. Number of moles of solids, number of moles of solids before dilution equal number of moles of solids, number of moles of solids after dilution, because in the process of dilution, number of moles of solids and number of equivalent of solute is unchanged. Only concentration and volume of the solution is changed. But molarity, number of mole divided by volume of the solution. From this number of mole equal molarity times volume, or concentration of a solution equal number of mole divided by volume of the solution. Now, initial moles of the solids equal initial concentration times initial volume of the solution. C1 times V1 equal number of moles of solids after dilution is final concentration times final volume. C final times V final, or most of the time concentration of a solution is given by molarity. You can write this as M1 times V1 equal M2 times volume 2, final volume. This is dilution equation. Example, how do you prepare 500 milliliter of a 0.4 molar of sodium hydroxide? What is given? Molarity of the solution and volume of the solution is given. You are asked to calculate mass of the solid. How do you prepare 500 milliliter of a 0.4 molar of sodium hydroxide? Molarity by definition, capital M equal number of mole divided by volume of the solution. From this, number of mole is mass of the solids divided by molar mass times volume of the solution. Mass of the solid, small m, equal molarity of the solution times molar mass times volume. Molarity of the solution times molar mass of the solid times volume of the solution equal molarity of the solution is 0.4 mole per liter. 0.4 mole per liter times molar mass of sodium hydroxide. Sodium, its atomic mass is 23. Hydroxide, oxygen 16, hydrogen 1, total 40 gram per mole. 40 gram per mole times volume of the solution 500 milliliter. In liter is 0.5 liter. 0.5 liter. Liter will be cancelled by liter. Mole by mole. Therefore, 0.4 times 40 times 0.5 is 8 gram, equal 8 gram. 8 gram. The question says, how do you prepare 500 milliliter of a 0.4 molar of sodium hydroxide? What do you do? To prepare this solution, weight 8 gram of sodium hydroxide, then dissolve in enough water until final volume of the solution is 500. Students, let us try this question. You have 3 minutes. Welcome back again, students. Let us do together. How many milliliters of 3 molar sulfuric acid are needed to make 450 milliliter of 0.1 molar sulfuric acid? Now this is dilution. Therefore, from dilution equation, we have molarity 1 times V1 equal molarity 2 times volume 2, V2. What is given? Initial concentration, initial molarity. M1 is 3 molar. V1 is unknown. Final volume and final concentration is given. Molarity 2, M2 is 0.1 molar. Final volume V2 is 450 milliliter. 450 milliliter. You are asked to calculate the initial volume V1. Therefore, V1 equal molarity 2 times V2 divided by initial concentration, initial molarity. Molarity 2 is 0.1 molar times V2 is 450 milliliter divided by initial concentration is 3 molar. 3 molar. Molar will be cancelled by molar. We are left with milliliter, which is the units of volume. Therefore, 0.1 times 450 divided by 3 is 15 milliliter. 15 milliliter. This is initial volume of the solution. Colligative properties of a solution. Colligative properties are those properties which depend on total amount of solute or total concentration of a solute, not depend on nature and kind of solute. Colligative is a Latin word meaning collective. The 4 most important colligative properties of a solution are vapor pressure lowering, denoted by the symbol delta P, vapor pressure lowering, which depends on amount of solutes or concentration of solute. Boiling point elevation, denoted by the symbol delta TB, boiling point elevation. Freezing point depression is delta TF, freezing point depression. Lowering in freezing points and osmotic pressure. Osmotic pressure. These are the 4 most important colligative properties of a solution that depend on amount of solutes or concentration of solutes, regardless of the kind or nature of solutes. Let us see each one by one. Vapor pressure. Addition of a solid solute into a solvent lowers its vapor pressure. Why? Because, look, this is a beaker containing pure water. Pure water. This is a beaker containing solution. Solution. Non-volatile solid solute is dissolved in water. Solid plus water. Solute plus water. Plus water. This is non-volatile. Non-volatile. No tendency to escape from this solution. If you look at this pure water, those water molecules with enough kinetic energy can be converted into vapor. Therefore, here we have high vapor pressure. But when we come to the solution, the fact that solute dissolve in a solvent is that there is solute-solvent interaction. Now this interaction, which is solute-solvent interaction, reduce the vapor pressure of this solution. Therefore, here we have small vapor pressure, low vapor pressure. We can say the vapor pressure of a solution, is lower than that of the pure solvent. The relationship between solution vapor pressure and solvent vapor pressure is expressed by Raoult's law, which states the partial pressure of a solvent over the solution, vapor pressure of a solvent over the solution, which is P of the solution, equal is given by the vapor pressure of the pure solvent times the mole fraction of the solvent in the solution at constant temperature. Therefore, vapor pressure of a solvent over the solution, according to Raoult's law, equal mole fraction of the solvent, times vapor pressure of a pure solvent. Mole fraction add up to give 1. Therefore, mole fraction of the solid plus mole fraction of the solvent equal 1. From this, mole fraction of the solvent equal 1 minus mole fraction of the solid. In a place of mole fraction of the solvents, we can use this 1 minus mole fraction of the solid. Therefore, P of the solution equal mole fraction of the solvent is 1 minus mole fraction of the solid times vapor pressure of pure solvent, P naught of the solvent. P of the solution equal 1 times vapor pressure of pure solvent is P naught of the solvent, vapor pressure of pure solvent, minus P naught of the solvent times mole fraction of the solid, P of the solution equal P naught of the solvent, minus mole fraction of the solid times vapor pressure of a pure solvent, mole fraction of the solid times vapor pressure of a pure solvent, P naught of the solvent. We can write this as P naught of the solvent minus P of the solution, P naught of the solvent minus vapor pressure of pure solvent over the solution, P of the solution equal mole fraction of the solid times vapor pressure of a pure solvent equal P naught of the solvent minus P of the solution is lowering in vapor pressure, or vapor pressure lowering, denoted by the symbol delta P, which is an example of Kaligati properties of a solution which depend on amount of solute. Therefore, it is lowering in vapor pressure, not vapor pressure, is an example of Kaligati properties of a solution. Example, the vapor pressure of a pure solvent is 0.4 atmosphere. What is given? Vapor pressure of pure solvent equal 0.4 atmosphere. When 0.5 mole of a non-dissociating solid is dissolved in 1.5 mole of the solvent at the same temperature, the constant lowering of vapor pressure is dash. You are asked to calculate lowering in vapor pressure, delta P. Delta P, lowering in vapor pressure, equal vapor pressure of pure solvents, P naught of the solvent, minus vapor pressure of the solution, equal mole fraction of the solid, times vapor pressure of a pure solvent, P naught of the solvent. Mole fraction of the solid is number of mole of solid, which is 0.5 mole of non-dissociating, 0.5 mole, divided by, because mole fraction of the solids by definition is number of mole of solute divided by number of mole of solution. 0.5 divided by total number of mole of the solution is 0.5 plus 1.5, 0.5 mole plus 1.5 mole times vapor pressure of pure solvent, which is 0.4 atmosphere. 0.4 atmosphere. Now the lowering in vapor pressure, delta P equal 0.5 divided by 0.5 plus 1.5 is 2 mole. Mole will be cancelled by mole. Mole fraction has no unit. Therefore, 0.5 divided by 2 times 0.4 atmosphere is 0.1 atmosphere. 0.1 atmosphere. Vapor pressure of a solution is lowered by 0.1 atmosphere because, as we said, addition of a non-volatile or non-dissociating solid into a solvent lowers its vapor pressure. You see, vapor pressure of a solution lowered by 0.1 atmosphere. This is delta P of this solution. Boiling point elevation. The addition of a non-volatile solid to a liquid will reduce its vapor pressure. Such a solution must be heated to a higher temperature than the pure solvent for its vapor pressure to be equal to its external pressure. For example, look at these two beakers. This beaker contains pure water. Pure water. The second beaker contains solution. A non-volatile solute dissolve in water. This is solution. Solute plus water, solvent. Solid plus water. We know that water boils at 100 degrees centigrade. Water boils at 100 degrees centigrade. Boiling point of a liquid is the temperature at which vapor pressure of a liquid equal external pressure. Water boils at 100 degrees centigrade. What does this mean? At this temperature, at 100 degrees centigrade, vapor pressure of water equal its external pressure. In this case, we say water boils. Addition of a solute into a solvent lowers its vapor pressure. Therefore, this solution must be heated to a higher temperature so that the vapor pressure of this solution equal its external pressure. Boiling point of this solution elevated. Now, boiling point elevation delta TB. Boiling point elevation delta TB equal boiling point of the solution TB. Boiling point of the solution minus boiling point of a pure solvent T0 B, where delta TB is boiling point elevation. TB is boiling point of the solution. T0 B is boiling point of pure solvent. The change in boiling point is proportional to the molality of the solution. Delta TB is directly proportional to molality of the solution. This proportionality constant is known as boiling point elevation constant, which is denoted by the symbol Kb. Therefore, we can write this as delta TB equal Kb times molality of the solution. You see? Boiling point elevation equal boiling point elevation constant Kb times molality of the solution, which is an example of Kaligati properties of a solution because it depends on amount of solids, concentration of solids. One way of expressing concentration of a solution is molality equal equal delta TB is boiling point of the solution. Boiling point of the solution minus boiling point of pure solvents. Delta TB equal Kb times molality equal boiling point of the solution minus boiling point of pure solvent. Example. Calculate the boiling point of a 0.33 molar solution of solids in benzene. Boiling point elevation constant of benzene is 2.53 degrees centigrade per molar. Boiling point of pure benzene is 18.1 degrees centigrade. You are asked to calculate boiling point of the solution. Therefore, delta TB, boiling point elevation equal boiling point of the solution minus boiling point of a pure solvent T0B equal Kb times molality of the solution. Kb times molality of the solution. You are asked to calculate boiling point of the solution. TB, boiling point of the solution equal Kb times molality. Kb times molality of the solution plus boiling point of a pure solvent equal Kb is boiling point elevation constant of benzene is 2.53 degrees centigrade per molar, 2.53 degrees centigrade per molar, times molality of the solution is 0.33 molar, 0.33 molar, plus boiling point of pure solvents, which is 18.1 degree centigrade, 18.1 degree centigrade. Molar will be cancelled by molar. Therefore, boiling point of the solution equal, boiling point of the solution equal 2.53 degree centigrade times 0.33 plus 18.1 degree centigrade is 18.93 degree centigrade. You see, pure benzene alone boils at 18.1 degree centigrade. When a solid dissolves in the solution, boiling point of the solution elevates to 80.93 degree centigrade. Therefore, boiling point of a solution is greater than that of a pure solvent. Freezing point depression denoted by the symbol delta TF. When a solid dissolved in a solvent, the freezing point of the solution is lower than that of the pure solvent. For example, pure water freezes at 0 degree centigrade. 0 degree centigrade. But if a solid dissolve in this water, the freezing point of the solution is depressed. Therefore, freezing point of the solution is less than freezing point of pure solvent. Now, freezing point depression delta TF, freezing point depression delta TF equal freezing point of pure solvent T0 F minus freezing point of the solution TF. This shifts of the freezing point is called freezing point depression. The change in freezing point delta TF is directly proportional to molality of the solution. This proportionality constant is known as freezing point depression constant, which is denoted by the symbol Kf. Therefore, we can write this as delta Tf equal Kf times molality of the solution, where Kf is freezing point depression constant times M is molality of the solution, equal delta Tf is T naught F minus Tf. T naught F is freezing point of pure solvent minus freezing point of the solution. For example, calculate the freezing point of a solution that contains 60 gram of urea. Molar mass of urea is 60 gram per mole in 500 gram of water. Freezing point depression constant of the solvent is 1.86 degrees centigrade per molar. You are asked to calculate freezing points of the solution. Now, delta Tf, freezing point depression, lowering in freezing point, equal freezing points of pure solvent T naught F minus freezing point of the solution Tf, equal freezing point depression constant Kf times molality of the solution. Now the solvent is water. We know that water freezes at 0 degrees centigrade. Therefore, T naught F is 0 degrees centigrade. This is 0 degrees centigrade minus Tf equal Kf times molality of the solution. Kf times molality of the solution. Minus Tf, or Tf equal minus Kf is 1.86 degrees centigrade per molar, minus 1.86 degrees centigrade per molar times molality of the solution. Molality by definition, small m, is number of mole of solute per kg of solvent, but number of mole of solute is mass of solute divided by molar mass times kg of kilogram of solvent. Mass of the solute urea is 60 gram, equal 60 gram, divided by molar mass of the solute. The solute is urea dissolved in water. Its molar mass is 60 gram per mole, 60 gram per mole, times mass of the solvent in kg. 500 gram of water in kilogram is 0.5 kilogram. Gram will be cancelled by gram. By 61, this is 1 over 0.5. Therefore, this is 1 over 0.5 mole per kg, mole per kilogram. Tf equal minus 1.86 degrees centigrade per molar. Mole per kg is molar. This is molar. Mole per kg is molar. Now molar will be cancelled by molar. We are left with degree centigrade, which is the units of temperature. Therefore, minus 1.86 degrees centigrade times 1 over 0.5 is minus 3.72 degree centigrade. You see, water freezes at 0 degree centigrade. When urea dissolves in it, freezing point of the solution become minus 3.72 degree centigrade. Therefore, freezing point of the solution is lower than that of a pure solvent. Osmosis and osmotic pressure. pressure. Osmosis is defined as it is the movement of solvent molecules from a less concentrated solution into a more concentrated solution, or from water side into solution side through a semi-permeable membrane. Osmotic pressure denoted by this symbol, osmotic pressure. It is the pressure required to stop or prevent osmosis is known as osmotic pressure. This osmotic pressure is an example of Kaligati properties of a solution, because osmotic pressure equal molarity of the solution times R is universal gas constant times temperature in Kelvin, you see, is an example of Kaligati properties of a solution, because it depends on concentration of the solution, molarity. Capital M is molarity of the solution. R is universal gas constant having a volume R equal 0.082 atmosphere liter per mole Kelvin. T is temperature in Kelvin. Therefore, osmotic pressure equal molarity times R times temperature. For example, calculate the concentration of a solid particle in human blood if the osmotic pressure is 7.53 atmosphere at 37 degrees centigrade. You are asked to calculate concentration of the solution. Osmotic pressure equal molarity times R times temperature. From this concentration or molarity, capital M equal osmotic pressure divided by R times temperature. Osmotic pressure of this solution is 7.53 atmosphere. 7.53 atmosphere divided by R is universal gas constant having value 0.082 atmosphere per mole atmosphere liter per mole Kelvin. Mole times Kelvin times temperature in Kelvin. 37 degrees centigrade temperature in Kelvin equal temperature in degree centigrade plus 273. Degree centigrade is 37. 37 plus 273 is 310 Kelvin. 310 Kelvin. Kelvin will be cancelled by Kelvin. Atmosphere will be cancelled by atmosphere. We are left with mole per liter, which is the units of concentration, equal 0.3 mole per liter, known as molar. This is concentration of this solution having an osmotic pressure of 7.53 at a temperature of 37 degrees centigrade. Students, in our today's lesson, we learned dilution. Dilution is a procedure of preparing less concentrated solution from a more concentrated solution. In the process of dilution, number of moles of solute is unchanged, but concentration and volume of the solution is changed. Kaligati properties of a solution are properties that depend on total amount or total concentration of solute particles, but not on the kind and nature of solids. The four most important Kaligati properties of a solutions are vapor pressure lowering, boiling point elevation, freezing point depression, and osmotic pressure. This brings us to the end of our today's lesson. Until next time, goodbye.